Okay, a warm good evening to everyone. It's already 6:06, so let us start with the session in the interest of time. So today's session, we are going to see about the actuation process that is involved in robotics. Till now, we have dealt with the microprocessors, sensors, microcontrollers, and perception. So these all were the parts of like up to the processing part when it is like if you compare with the analogy, so it is like once your human brain sees stimuli, it has processed, and after processing, what happens is this process actuation is an analogy to this process. So this session will be handled by my friends Vishwanath and Varun. So over to you, Vishwanath and Varun.
Yeah, okay. Thank you, Dheeraj. That was a good introduction. So, hi guys, welcome. So, how was all your session till yesterday? So, we'll have a small chat before we start with actuators. So, did you understand everything about sensors? First, MPM, microprocessor, microcontrollers, sensors, and then Tinkercad. Did you explore Tinkercad? How many of you explored Tinkercad? How many of you tried out different circuits? Yeah, you can unmute and speak. There's nothing wrong. Am I audible first of all?
Yeah, you are audible.
You're audible.
Okay. So why is everyone silent? So
Guys, if you don't wish to speak, you can also just interact with us in the chat.
Yeah. So yeah, that's my friend Varun. So I'm Vishwanath, third year EC Cyber Physical Systems, and we are here to teach you about actuators. So before explaining what an actuator is, let's go by the analogy of what's a role of an actuator from the hot pan example that Tarun told you in sensor session. So for sensors and perception, if you remember correctly, Tarun explained you about the hot pan example, right? Can anyone tell me what that example was? Guys, come on, interact. Do anyone remember that example?
Guys, we need you to interact, guys, because the session will be more interesting if only if you would interact. So come, let's make it interact, guys. Come on.
Oh, stimuli. Okay. Could you please elaborate a little bit what that example was? Okay, let's not take too much of time. So it was basically you sensing is like there is a hot pan. You let's say accidentally you touch the hot pan. The sensor receptors in your skin feels the hotness, right? That's sensing. Okay. So in a robot, taking analogy to this example, this skin touch is your sensing part. So that, yeah, when we touch up, okay, our hands, wow, very good. Yeah, exactly, yes. So what happens is that your neurons transmit this message fast using synapses, and that reaches your brain. So your brain is the micro controller in the robotic circuit, like in the analogy that processes what's gonna happen, how should you react to that, and sends a control signal. What is it? Control signal. It sends it tells all the muscles present in our arm to retract back, to take the hand back from the hot pan, right? So this action of taking the hand back is called actuation, and actuators are present to act upon the physical environment present outside based on the control signal received from the microcontroller. So are you clear with this example? So we can go to next slide, Varun. Yeah, basically that's the definition. So an actuator is a device that produces a motion by converting energy and signals going into the system. It requires a control signal and a power source. So mostly if you see in robots, what will be the common actuator elements? What do you think will be common actuator elements? Like actuator acting upon it, motion, you can easily guess some robotic elements. Any guesses? Just like fast guesses. Come on, guys, be fast. We'll finish the introduction fast. Limbs, bar, wheels. Okay. Anything else? Oh, that's a clue. That's a clue in the PowerPoint. It needs a power source. It needs a power source. Something that requires a control signal, power source, motion, energy. Any guesses? Motor. Wow, super macha. Who's that? Venkat Ramanji. Way to go. Yes, motors. Motors are like stepper motor. Yeah, stepper motor, servo motor. These are the motor is it's a very good example for an actuator. Yes, exactly. So it requires a control signal and a power source. The motion that an actuator produces can either be rotary or linear motion. So we'll learn this as we learn about the types of actuators. And these actuator elements are usually the source of torque or power. Okay. So actuators that you find in daily life. So what can it be? Okay. So if you have traveled in buses, in public buses, so yeah, there is an actuator there. If you find that there is a motor linked to the door of the bus for closing and opening, right? So that motor has a rod connected to it to the door of the bus, to one side of the door of the bus. So that actuation there is a good example for linear actuator. It opens the door, it closes the door in a linear motion, with the linear motion. So that's basically a good introduction to actuator. So can we go to the next slide, please? Okay, flow diagram of actuator. So this is just basically explaining you how technically it works. So as I said, you send a control signal. Control signal is something, you know, that tells the actuator to what? Sliding door. Yeah. Sorry, sliding door. Okay, so control signal is something that instructs the actuator to produce this much amount of actuation, because you see you cannot continuously actuate on things. You need to restrict the motion. So that is being handled by the control signal, and your energy source is the one that provides the energy for the actuation. So that is being received by the power amplification module, and that electrical energy or the, let's say, pneumatic actuation, or in you'll see it in type of actuators where different types of energy are converted into motion. So that energy conversion happens there, and that in the end produces a mechanical change or motion, and that is the output that you receive from actuator. Yeah. So Is everyone clear with this? Any doubts? So that's the complete introduction on actuators. So everyone got it? Can I get a yes in chat? Clear. Okay, thank you. So we'll go to the next slide. Yes, thank you. We'll go to the next slide, please.
Okay. So hi guys, I'm Varun. And before we go to the next slide, which is going to be types of actuators, I want you to find out what can be the types of actuators. Like, look at the current flow diagram visible on the screen. So the control signal to whatever actuator you want to make, the control signal is always going to be same. It's either going to be an on or off or something. But there are few things over here, depending on which the type of actuator you'll use will change. So there are two variables in this. What do you think the possible variables are? Any answers in the chat? Okay, that's a good answer. Depends on the power source. That is one of the answer. What do you think the other is? What is the other variable over here? Amplification factor, not so much. Yeah, depends on the power source or the type of energy conversion. That's correct. So yeah, the other category on which you would decide an actuator is based on the output, whether you want an output to be in a linear mechanical motion or do you want it to be in a rotatory motion. So yeah, that's what we're going to see in the next slide. So first, the types of actuators based on the source of energy. So we have three types of actuators over here. You have hydraulic, you have pneumatic, and you have electrical. So hydraulic is pretty simple, as you might have already known. You get the energy is converted from the compression of fluids, the energy present over there, into a mechanical motion. And pneumatic actuators, the energy is similar to hydraulic, but instead of the fact that it's compression of liquid, over here you have compression of air. So in pneumatic actuators, you have compression of air, which is converted into mechanical energy. And then finally, you have electrical actuators, where the energy is converted from electrical to mechanical energy. So this is one type of categorization which we can do for type of actuators, which is based on the source of energy. Next, we have based on the type of motion. That is, whether we want the actuator to give a linear motion or do we want the output motion to be rotatory in nature. So yeah, now that you have seen what all types there can be, let's go right into our first type, which is pneumatic actuators. So pneumatic actuators are devices that convert the energy of compressed air or gas into mechanical motion. The keywords being, you convert the energy from compressed air. It's not from normal air because energy is only in compressed air, and you convert that to a mechanical motion. So if you can see this diagram over here, what's present over there is that you have a small piston and then there are two chambers over here. These two chambers are empty, and from this extend port you have air coming in over here, and from this retract port you have air leaving over here. So now, what is the change in energy over here, and what do you think the type of motion that is? Is it linear or rotatory? And yeah, is it linear or rotatory? Guys, what do you think the output, the type of motion you get in this cylinder over here? Yeah, perfect, linear, because when air comes through this extend port, the piston is pushed over here, and from here you get the output, the rod extends, and that's a linear motion. So the basic characteristics present for a pneumatic actuator it derives power from compressed air. It has a small response time. Response time as in, when you pump air into this extend port, it immediately pushes the head of the piston over here, and that immediately pushes the rod outside, which gives you your output motion. So there's the time between you sending air into this chamber and you getting your rod out is very fast. That's why it's often, these pneumatic actuators are often used in places where you need a quick change in like on and off motion, like when you quickly want it to switch on or off. And the third characteristic is that it has minimal leakage. So even though you pump air into this extend port, there will always be a small amount of air which leaks, even though it's not that much, but over a long time when you use it in industry, it will still cause leakage. But in pneumatic, it's very less. So now have all of you understood how it's basically, how pneumatic actuators basically work? If so, we can move on to the next slide. Okay. So when you want a linear motion from a pneumatic actuator, there are two types in which you can get. So the first mechanism in which you can get a linear motion is called single acting, and the second will be called double acting. We'll be seeing that in the future, but for now, let's see what a single acting linear pneumatic actuator is. So this is a very simplified drawing for the pneumatic actuator, where this is the chamber where you have your air, this is your piston head, and this will be the rod over here. So now what happens? When you send air over here, this piston will slowly move over here and the rod extends out. But you want the rod to come back in for future thing. You don't always want it to be permanent in this position. So you have a spring attached over here. That's what is meant by single acting. As in the fact that you send air only through one chamber over here. And when you want to, that is when you send the air inside, it goes into on, that is the piston extends out. And when you want to be in off, all you have to do is remove the air from this chamber, that is stop supplying new air. And this spring, it will push out the piston head. That is when the energy from the compressed air is greater than the spring energy, the energy contained in its compressed form of the spring, the rod extends outward, which is on. And when the spring energy becomes greater than the compressed energy, the spring goes back in, it extends, and it's in off mode. And here you have two types of cylinders called minus or plus. This minus is in the fact that the spring is present in this chamber. That is, you send air in to extend the rod, and the spring is there to push back the rod. Now, I have one question for you. Suppose, let's say the spring was not present over here and that there is air in both chambers. Now, you'll be supplying in some air through this valve over here and you'll be pushing the spring out. Let's say that is called extend energy. That is extend force because it's extend port. So let's say this force you send in air over here, compressed air, and it pushes out. This is called extend force. And now let's say you send air towards the retract port also to push it out. Let's say that is called retract force. Which energy supplied do you think would be less for the same amount of force? As in, you send air over here, it will contain some energy in its compressed form. You send air in over here also, and that will also have an energy. For the same amount of force, which do you think will have lesser energy? Any answers? Okay, let me give you a small hint. So, do you see this area over here? This is called the bore area. That is the area covered by the head of the piston. So this area is called the bore area. And over here, if you see the contact area, it is not full bore area. It is bore area minus this piston area. This piston, even though it's small, it will still take up a small bit of area. So the full area covered by this place is bore area, and this place will be bore minus your piston area. And F is equal to pressure into area. So which force do you think will be greater for the same pressure? That is for the same energy. Yeah, perfect. Extend port. Because this will always have greater energy. That's why when you need to extend the piston, you always need to apply, sorry, excuse me. When you need to extend the port, when you need to extend the piston, you always need to apply lesser area than this. So that's why over here in this minus configuration, you have a spring over here. So that this, because when you constantly extend and contract the spring will lose its elasticity after some point. That's why in industrial places, generally minus is recommended because the spring is using a lesser amount of force. And so the spring loses elasticity less. So yeah, that's all there is in single acting linear pneumatic actuator. Next, we'll move on into double acting linear pneumatic actuator. So over here, as you can see this GIF, you have, first of all, there is a chamber over here, and then there's a chamber over here also. But in this case, you do not have a spring. Instead, both these areas are constantly being pumped with air, and the air is also getting sucked out of one chamber. So in one chamber, when you want it to extend, as you can see, the air is pumped in over here, and simultaneously the air is sucked out over here. And so due to the pressure difference, the pressure generated over here will be high, and so the piston moves out like this. Similarly, when you want the the piston to go back inside, that is when you want the rod to retract, all you have to do is suck out the air from the extension place, and you pump in air into the retraction chamber. So all this does is, in the single acting linear pneumatic actuator, you have to pump in and suck out air into one chamber. Whereas here, you suck in and pump out constantly from two chambers. Now, this is widely used in industries because over there you have wear and tear of spring and you have air leakage. But in this place, since you're constantly monitoring both the chambers, you'll never have any wear and tear of like mechanical parts. So yeah, this is double acting linear pneumatic actuator. The double acting pneumatic cylinder has two ports that control the movement of the rod. The compressed air causes the rod to move in two directions by extending and reacting without the assistance of the spring. That's what we saw earlier. So in both of these motions till now, we have only been seeing linear mechanical output. That is the rod over here. It extends linearly and it retracts linearly. But what would you do if you want an angular rotatory motion? Let's say your, how do I say this? Okay, let's say that you want your rod, which is your output load, you want your rod, instead of going forward and backward, you want it to move by a certain degree. In that case, what would you do? Now there, we use something called rotatory actuators. So the only difference is that over here in rotatory actuators, the output, instead of being linear, it's rotated. So there are two methods in which we can get this. There are two mechanisms. The first one is called rack and pinion, as visible over here. And second, we have what is called vane mechanism. So first, in rack and pinion, similarly to the linear thing, you have both types. That is, you have the single-sided with the spring, and you have the double-sided without the spring. That is, in both chambers, you constantly have air. So in this case, in rack and pinion, what happens? Do you see these grooves over here? present on this side of the wall. Like if you can follow my cursor, these grooves over here, yeah, these grooves are called the rack on both sides over here and over here. These grooves are called the rack, and the grooves present on the gear, these grooves are called the pinion. So what happens? This over here is the retraction, sorry, the extend port. And so when you let in air inside this valve, air fully occupies the space. And when it's no longer sufficient, that is when you constantly pump in more air, it pushes out in both directions. Over here, you have a simple screw and this chamber just pushes out. So, sorry, not a screw, you have a spring. You have a spring over here and this chamber pushes out. When you stop sending in air, this chamber again, when the energy over here is more, this chamber pushes in and all the air is sent out of this thing. So what happens in this case? The grooves of the rack are aligned with the pinion in such a case that when the chamber moves like this, the rack also rotates like, the pinion rotates like this in a clockwise, in an anti-clockwise direction in this case. So the rod over here, that is the load, it's connected axially towards this gear. Can you follow me? Like imagine that a rod is connected over here at this place and the rod is coming out of the screen. That is your load. So what will happen when this gear rotates? The rod coming out will also rotate anti-clockwise. Similarly, when you have the chambers pushing in, the piston pushing in, the gear will move clockwise and the rod will also move clockwise. So yeah, here also similarly you have a double-sided where instead of a spring, or you will send both the air towards the retract port and towards the extend port. So yeah, it's similar to that. Now this is one type of mechanism where it's you change based on the grooves, and it's called rack and pinion. Are everyone following me until now? Does anyone have any doubts? Like, are you able to visualize how the load is supposed to move when this gear moves? Yeah, just drop a message in the chat if all of you are clear and you don't have any doubts. Yeah, perfect. Okay, so now we'll move on to the next mechanism through which you can get a rotatory motion through a pneumatic actuator. So in this method, you have a rack and pinion. The next method is called vane. So in this, what happens? Over here, you don't have any grooves. Again, the rod over here is connected axially towards this. So imagine in the center place over here, you have a rod which is just coming out of the screen. That is, the rod is connected in the z-axis. Over here also, the rod will be connected over here and over here simultaneously. So you have two chambers over here, P1 and P2. You can think of it like the extend port and the retract port. So here what happens? When you'll be sending air over here through the, let's say you send air towards P1. So air comes into this chamber. There's currently no air in P2. Only air is coming in through P1. So what will happen? Slowly air will start filling in all spaces and it will push this vane over here. You see this block over here? Yeah, this is exactly called the vane. So it will start pushing this thing. When it pushes the vane towards P2, you will have this motion. And when this happens, the rod, can you imagine how the rod will move in the z-axis? So the rod in this case will move clockwise. And now, let's say you wanted to move anti-clockwise. All you have to do is you can either suck out air throughout P1 or you can send in air at a higher pressure in P2. And then once this pressure is sufficiently greater than this pressure, this vane will slowly move towards P1. And that you can see over here in this motion. This will be counterclockwise and the rod will also move counterclockwise. So what do you think the major difference will be in rack and pinion and in vane? Both of them use air, compressed air, to get a mechanical output, and both of them have they give out a rotatory motion. What do you think will be the difference? There is one major difference if you look at both of these images very closely. So over here you can see the rack and pinion constantly move, and here in this diagram you can see the vane constantly move like this. What do you think is the major difference over here? Any answers? It's okay if you say the wrong answer also. There's no punishment. So like, feel free to guess whatever you think is correct. What is the major difference between using a vane mechanism and a rack and pinion mechanism? No answers? Okay, let me tell it myself. So the main difference between both of these is you can manipulate the number of grooves present in the rack and pinion to get a turn more than 360 degrees. That is, you can make it rotate more than one rotation in a rack and pinion. But over here, if you see clearly in the vane, you can get it to move only by a certain degree over here. It cannot make one full rotation also. It can't even make 360 degrees rotation. It comes somewhere usually till 330 or something like that, 300 to 330. You can't even make one full rotation. The object will move from here to here or from here to here. Whereas if you look over here in rack and pinion, you will also see that based on the number of grooves present, you can make it to turn how much ever you want. Rack and pinion has friction loss. Yeah, that is also present. You will have friction. Sorry, you'll also have friction loss over here. But then here also there is a friction loss present. You will be either ways lubricating both of them. So yeah, there'll be a minor difference in friction loss, but the main difference is that rack and pinion will allows more than one rotation, one complete rotation, whereas in vane you do not have that. The rotation will always be less than 360 degrees. So yeah, that's all we have in pneumatic actuators. Any doubts before we move on to the next topic? Yeah, Avantika, and vane you can move it both ways. Like if you change, if the pressure in P1 is more than P2, it moves clockwise. And if the pressure in P2 is more than P1, it moves counterclockwise. So in both mechanisms, you can move it clockwise or counterclockwise. Okay, so if you don't have any doubts, let's move on to the next topic. Hydraulic actuators. So hydraulic actuators are very similar to pneumatic actuators. The only difference between them is that over here in hydraulic actuators, you have a fluid. Sorry, not a fluid. You have a liquid present over here. That liquid can be water. It can be any chemically synthesized liquid based on how much PSI you want to work it under. So yeah, whereas in pneumatic, you'll be using compressed air. That's all the differences. Every type, like the mechanisms here also, you'll be using vane and rack and pinion for rotatory motion. And here also you'll have the similar single-sided and double-sided mechanisms for linear motion. As in, you'll have two chambers over here where you manipulate with fluids, which is double-sided. Or as you can see over here in this diagram, you have a spring in one thing and you have the fluid in one chamber. So yeah, hydraulic actuators are devices that convert the energy of compressed liquid into a mechanical motion, as we saw. So yeah, let me explain quickly what's happening in this diagram over here. You have a cylinder, you have a spring, and this will be plus. Because if you can see over here, the spring is present in the chamber where when the spring is compressed, the the rod goes in, that is the rod retracts. And if the spring is fully extended, the rod extends. So yeah, this is a plus configuration. And over here you have hydraulic fluid, a piston, and a supply and return line. So this stem is the same thing as rod. It's just a different terminology. So what happens over here? When you pump in fluid, that is hydraulic liquid through this, once the energy of this is greater than in the spring, this rod slowly comes up. And when this retracts into the chamber, you see this opening over here, this gets opened. And this is basically the control valve is in off position. That is, this chamber, the liquid or whatever is present in this chamber can freely interact with this chamber. And now, when you stop supplying liquid into this chamber, or when you retract liquid from that chamber, the energy present in this spring, the energy present in this compressed spring, it becomes greater than this. And so the rod slowly extends out. And when it extends out, you can see based on the grooves over here, that this structure neatly fits into this structure. And so it's completely closed. That is, the control valve is in on position. So yeah, that's all that's happening here. This is more of an application, but the same idea exists that due to compression and retraction of this spring, this fluid and based on this pressure present inside this fluid, the piston moves up and down, and so you get a linear motion of this rod present over here. So yeah, in this also you have the same types of single acting, double acting, rotatory, everything is similar. The only difference will be that you have a liquid present and not a gas present in that chamber. But wait, before I start semi-rotatory actuators, if all the mechanisms in hydraulic actuators and pneumatic actuators are same, that is, we have the same rack and pinion, same vane, and same single acting and double acting, why would we choose hydraulic over pneumatic, or why would we choose pneumatic over hydraulic? What advantages do you think both of them have? If you look at the characteristics of pneumatic actuators, which I told you at the starting of the concept, if you look at these three characteristics, you can get a clue of why we would choose one over the other. Any clues? Okay, yeah, definitely there is minimal leakage in pneumatic actuator because gases tend to leak much less than liquids. So that's their minimal leakage. Power will be more in hydraulic. Yeah, that's true. Why do you think the power will be more? Actually, I won't say the power output would be more, but the power which you get for a certain energy input, that is, if you let's say you send 500 meter cube of 500, just say you send 50 meter cube of fluid, that is of liquid over here, and you send 50 meter cube of air over here, for the same input amount you will have a different power output. But yeah, that is true. Power will be more for the same output. But yeah, why do you think that is so? Any clues? That point over there, that power will be more in hydraulic. That is the main reason why we use hydraulic over pneumatic in certain situations. But why do you think it will be so? Any guesses? Okay, I'll tell you why. So, in hydraulic actuators, the liquid which you send, it's definitely whatever liquid it may be, it's lesser compressible than gas, whatever gas you send. Because gas, are always more compressible than liquids. Yeah, due to incompressibility. Yeah, that's true. So let's say suppose you send certain energy for air and send certain energy for liquid. What will happen in the case of pneumatic actuators is that a certain amount of energy will be sent to compress the gas inside. Whereas in hydraulic, since it's not that compressible for normal use, that is like at high pressure it's definitely compressible, but for normal pressure which we use in industries, it's not that compressible. So for the same energy you'll get more power over there. Hydraulic could sustain power provided for a long time. Yeah, that is also true, because suppose you send a constant amount of pressure for a long time, that amount of energy which you send will compress the gas after a certain time. So let's say you have the limbs of a robot. Let's say you take a bipedal robot and you control the limbs using hydraulic actuators. You want your arms to be in a certain position for a, like, let's say you want to pick something, you want your arms to be at that position for a certain amount of time. You don't want your arms to constantly be moving around. So when you want to make it to go and stay at one position, if like you take a hydraulic actuator, you send a certain amount of liquid, that's fine. But then if you take pneumatic actuator, there's a very small chance that some gas is compressed, and because of that the arm might move. So you will always, if you want your output to be stable, that is you want your arm to be stable or the load connected to be stable, you will always use hydraulic actuators. So yeah, that is one of the major reasons why people take hydraulic actuators. If it's for a light amount of load that you want to move, or let's say that in certain cases, you wanted to constantly switch on and off. Like it's a very light load and you want to constantly switch it on and off. So in that case, you will take pneumatic. Because a pneumatic, even though it can't support high load, it still is much more cost efficient as the leakage is minimal. And even if gas leaks, neutralizing that is very easy. Whereas if you take in this case, let's say some liquid, some chemically synthesized liquid, let's say that leaks, the cleaning and maintenance of that will be much more costlier. So while hydraulic is much more cost ineffective, it still has its advantage that it can give higher power for the same energy, and it can also give a stable output. So yeah, that's why you use it in hydraulic jacks and hydraulic brakes. So if you ever have like if your car ever punctured, you need to lift your car using a jack, right? So in that jack, you want your car to be lifted at a stable position. You don't want that jack to be constantly moving. So that case, you use a hydraulic actuator. And similarly in a brake, pneumatic actuators can't take that much load. If you want to stop a whole car, you need to like remove that full momentum. So that whole momentum gets transferred onto the brake. A pneumatic actuator can't take that much load. So yeah, that's all there is about hydraulic and pneumatic actuators. Does anyone have any doubts? No doubts? Okay.
Okay, then we'll move on with electrical actuators. So, coming to whose doubt was it? Krishna Narayanan. Okay. So, what was his doubt a long back? Does actuator require a feedback circuit? So now we'll answer that question soon. So in electrical actuators.
Wait, just 1 minute, sorry to interrupt. But then Venkatramanan J has asked a doubt. For spring to extend, do we suck the fluid out? So yeah, in that case, we always need to suck the fluid out, because for the spring to extend, the energy, that is the force provided by the spring, needs to be greater than the liquid pressure or there present. And if you don't suck the pressure out from the liquid, you can't reduce that. So yeah, you always need to suck the fluid out if you want the spring to extend. But even when you suck the fluid out, it will still be in one chamber. You don't use two chambers for that. That's why it's called single-sided. So yeah, that's it.
Okay, guys, do you have any more doubts? So we'll finish off uh, the doubts before moving to electrical actuators. Say okay, we'll be moving to electrical actuators now. So electrical actuator, as you guys guessed at the start, we use the famous motors. Yeah, they convert electrical energy into motion. So two main types of electrical actuators used for position control are servo motor and stepper motor. Many of you know about servo motor and stepper motor, but we'll learn a little bit in detail about them. So we'll go to next slide. So any guesses before? Okay, wait, go back. So before going to next slide, so what do you guys know about servo and stepper motor? So we'll first interact for a little bit and then we'll go, because after electrical actuator the session is over, so we'll have a little bit of interaction. What do you know about a servo motor, stepper motor? Any difference, anything unique? Hello, guys. Am I audible? Hello.
Yeah, you're audible.
Okay. So no one knows about servo and stepper. So we'll go further. Next slide. So first we'll go to stepper motor. So stepper motor is normal motors that you use for little toys. You see stepper motors almost everywhere. They are digitally controlled, so which means that you directly actuate the motor based on the input which you give digitally, which is a voltage, and you directly get the motion out as output. So it has no D to A converter, yeah, which is not required, but we need this in servo motor. We'll see why. Next, we don't have a feedback mechanism. So the main reason why we don't need a feedback mechanism in a stepper motor is we don't need to find the current position of the motor shaft, because stepper motor is mainly used for continuous stepwise rotation. So there, sorry, it's used for stepwise rotation, where you don't need to actuate to a certain position based on the current position. There's no such need in stepper motor, and hence you do not require a feedback mechanism. So it has low motor inertia, which enables quick start, and this is what you see in most robotic arms. You can also find servo motor in some robotic applications where your precision to the position is important. So that's where servo motor comes in play. So your stepper motor has low torque output. Low torque output means you have some disadvantage, which is actually a disadvantage for stepper motor. You can't use a stepper motor in important applications where you need a higher torque output. So going to servo motor. Can we go to the next slide? Yeah, so if you see in servo motor, you can find a small image of how a servo motor works. So you have a gearbox which can give out high torque with the gear ratio present. You have a DC motor that rotates at high speed. You have a potentiometer, something that you studied in the sensors class, right? Can you can you recall what was a potentiometer? Can anyone like tell me why we use a potentiometer here? Any guesses why we use a potentiometer here? Variable. Okay, variable resistance is the application of potentiometer, but to work on exact voltage. Okay, still more precise. I already told you the exact word when I was explaining stepper motor. Exact voltage. Think again. Measure voltage difference. Okay. Anything else? To work on exact voltage, we work on exact voltage to what? Why? To regulate the voltage for the correct degree. Exactly. Oh, super. Venkat Ramanji, thanks a lot. To regulate the voltage for correct degree of turn. More than that, to be precise, potentiometer we here use for feedback control. So with that, we achieve the exact position to which we need to actuate the servo motor to. So servo motor, a feedback control mechanism is present. So this is much reliable to actuate upon even if we have a change in load because it has position, a trustable position control. And we use PWM control signal to achieve the desired position for to to actuate the motor for the required degree of turn. And to get the exact position, we use duty cycle. Yeah, obviously 50% duty cycle accounts to almost 50% of the total turn. Let's say if you have 0 to 180 degree in a servo motor, your 50% duty cycle will rotate the gearbox such that your the angle of rotation will be 90 degrees. The servo will move to 90 degrees. So that's servo motor. So we'll go to next slide to see how exactly the servo motor works. Okay, stepwise rotation. When we give single excitation to okay, yeah, okay. So Gautam is explaining it in words. So we'll go to next slide. So I'll also show what Gautam is explaining as a small image after we see this servo motor working diagram. So we feed the desired input to the servo controller. So the desired input is the angle to which we need to actuate on. So that input is fed into the servo controller, which then sends signal to the drive amplifier. Drive amplifier sends required voltage for the DC motor to start the gears so that the gears start rotating. And that in turn gives a armature current, which again drives the drive amplifier. For the that's how the drive amplifier works. So now this DC motor, to find how much it has rotated, we use a encoder. That's basically what Tarun explained in the sensor session. So we find how much we rotated, get that output as an input and feed it to the servo controller. And this is called feedback mechanism. We get the output, feedback the input, compare the difference, and again actuate it. So that's the main work of the encoder. It gets the current position and speed of the DC motor and sends it to the servo controller. Now again, servo controller sends the signal to drive amplifier based on the difference obtained. So there will be a difference. So let's say we want to rotate it by 100 degrees. So first the DC motor would have rotated assume that it would have rotated the servo by 90 degrees. So the encoder will read that change. We know that it's 90 degrees. We need to reach 100 degrees. So the difference is 10 degrees. So now the 90 degrees is the input to servo controller. So it will find the difference. So the difference is a positive 10 degrees. So it will send that to the drive amplifier as the required voltage, and that will again drive the DC motor. This is how your servo motor constantly changes the output to match it to the precise required input. And your torque sensor senses the torque, so that let's say you need a minimal torque, you can control it via the torque sensor, which is optional. We don't use it much, but this position encoding is the main biggest advantage of servo motor, because servo motor is continuous rotation. So hence we need the exact position to know how much to actuate to, and the output is your normal motion. So yeah, that's all about electrical actuators. So does anyone here have any doubts? So any doubts? Guys, come on. Did you understand this first? Is it clear? Should I explain anything again? So any doubts? Okay. So can we consider can we consider stepper motor as analog input and servo motor as okay? Wait. Why do you consider stepper motor as analog input? We are giving we are driving the field inside the stepper motor. The field wires the field wires inside the stepper motor from the given voltage. So I already told you that we don't need a D to A converter, because well, wait, I don't get it. Why do you consider stepper motor as analog input? No, no, it's not analog input. Servo as digital input. Yeah, servo is digital input.
I guess what he means by analog input is that you can change it only by a certain finite amount. Like you can't change it by a variable amount as much as in a servo. Like in a stepper motor, I think what he means is that you can change
Okay,
it
wait,
only
instead.
by one
instead,
small
let
turn.
him unmute. Abhijit, why don't you unmute and ask your question? I'm not clear with what you're asking. Mic unavailable. Why da? Oh, wait, Dheeraj.
Just a second, I'll check with that. I have allowed mic for all attendees.
Oh wait, I guess in
I
his
think
PC mic is.
Tarun was able to unmute and speak. Okay. Once again,
Yeah, in
can you
his
take?
PC. Yeah. Yeah. No. I guess there's an issue with his PC. Okay, so if you could elaborate a bit, it'll be good. Uh, okay, so meanwhile, I'll show what Gautam, my friend Gautam, has texted in the chat for the stepwise rotation. So he spoke about single excitation to the coils and all those things. Those are so that's going a bit deep into how a stepper motor works. So we have like so much of classifications inside stepper motors, and I know it will be a bit too much theoretical and boring. That's why I didn't choose to take it today. So if you want, I can just show you some images of how it works. So basically, you have various various types of stepper motors, like two-phase stepper motors, variable reluctance stepper motors. So you have so much of classification. So yeah, I'll share an image with you. So oh wait, like servo stops immediately after we reach that particular input. Technically, it should do that. Yes, that is correct. But the biggest issue in servo, like practically when you make a robot, is that it will always have a little bit of overshoot. So when let's say the desired angle is 90 degrees, so there are practical cases where this has happened. Okay. So it will stop at 90, it should stop at 90 degree, but sometimes let's say if it overshoots by 92 or something, the encoder will detect that and it will try to bring it back to 90. But again, let's say it overshoots. So if you don't provide a proper PWM signal, an accurate PWM signal, the servo will not stop immediately after you reach the particular input. It will try to constantly adjust, which will make a constant vibration in the servo motor. And this example that I gave you of 0 to 180-degree rotation for 0 degrees to 100, so for 0 to 100 of PWM is just a vague example, because in some practical application for some servo motors, you need to give 2.5 to 12.5 for 0 to 180 degree of rotation. So it actually depends on the documentation that the manufacturer has provided to you for the servo motor. Technically, yes, what you say is correct. It should immediately stop after we reach the particular input, but practically, no, it doesn't. So, any other doubts? So, first, did you get your doubt clarified? Okay. Yeah, so the image that I shared there is what typical two-phase stepper motor looks like. So what you see there are internal windings and external windings. By what I said as by what Gautam mentioned there as excitation is where you give the current to the field windings present there, which will in turn create a magnetic field, which produces a magnetic flux, which rotates the motor, which rotates the rotor present in it. So you have two components, a stator and a rotor. Stator is something that is attached to the out, outside layer of the stepper motor, which doesn't rotate, as the meaning gives you. And rotor is one which rotates, causing a rotary motion. So yeah, that's what Gautam told about stepwise rotation. So yeah, anything else? Any doubts? Any more doubts? So are everyone clear? Varun, next slide. So yeah, guys, that's it. That's all about actuators. So yeah, thanks for attending the session. So if you have any doubts, you can ask it in the group. Please use the Discord server. We created the Discord server for you to ask your doubts. Be interactive there. You can also find the PPTs in the Discord server as well as in the WhatsApp group. Also, make sure you leave a LinkedIn post giving your feedback on how the session was. You can tag me, myself Vishnathar, and Varun Venkatraman in the LinkedIn. And oh, okay, we have some doubts here. And yeah, that's it, guys. So if you don't have any doubts, yeah, you're free to leave the session. Please do fill the form. Please do give your feedback. Why does the error occur and doesn't it occur in stepper motor? So in stepper motor, you don't care to achieve a proper position, Venkatraman. You just continuously rotate it. That's all. Why does the error occur? So it's because, let's say, to reach 90 degrees, let's say you need to give X amount of input. Let's say you need to feed X voltage. Okay, let's assume it. But there will always be a voltage drop due to the internal impedance of the circuit. Okay, internal impedance is like internal resistance of the circuit. So let's say you feed X voltage to the servo motor. So let's say there is a component that like consumes around some point voltages. Okay. So now what does the servo receive? X minus the loss. Let's say you need to feed 5 volt. Let's say 0.1 is gone. So the servo receives just 4.9 volts. So with 4.9, will it achieve 90 degrees? No, it won't. So it will stop there. So again, you feed 5. You don't need 5 to move. So you just need 0.1. So what happens? It should take the 0.1, but in practical cases, sometimes it will take the 0.1 and sometimes it will take more than 0.1, making it to overshoot from 90 degrees. So again, what will happen? You need to come back. So this is the main issue. The main issue arises due to the internal impedance of the circuit. So there are like various factors that makes the error occur. One is internal impedance. The second is the load to which the servo motor is connected with. The load will it itself will have an impedance, and that might also have a effect on your servo's position. Doesn't it occur on stepper? No, because in stepper you don't care on where you stop. You just care about just rotating it. You don't need to know the position in servo. Sorry, in stepper. You just need to know the position in servo motor. So is it clear? Yes. Okay. Yeah. Thank you.